Hello, this is Mrs. Gabriel. I will be presenting to you Chapter 19 for AP Environmental Science class. This chapter focuses on global change. So we're going to open with our picture of polar bears and little Arctic foxes and talk about all these little critters. Polar bears are predators that eat seals. So what the polar bear does, he looks for holes where the seals come up for air, and then they pounce on them. They only eat the blubber, the highest energy material, leaving the other parts behind, like the Arctic fox. The Arctic fox eats the other food sources. Natives, indigenous people eat the polar bear and use it for its fur to survive. Scientists have taken satellite photos showing a retreat of the polar ice caps, which we'll be looking at in this presentation in a little bit. They always retreat a little in the summer, but because of the rise in Arctic temperatures, the amount of summer shrinking and of the ice has increased, and the ice is considerably thinner, which is making it more vulnerable to future melting. As the polar ice caps melt, the polar bears lose their habitat. They can't even get to some of the sea ice to hunt for the seals. The sea ice also melts 3 weeks earlier than it did 30 years ago. As a result, the males weigh less these days. If polar bears become extinct due to loss of habitat due to Arctic sea ice disappearing, the seal population could increase. The Arctic fox will, and that's our Arctic fox that we're looking at, will decline. The indigenous people and their resources and culture and social identity will be negatively affected, and the entire Arctic food web will be impacted. In 2008, polar bears became classified as threatened species because of the decline in their ice habitat. In this presentation, we will examine the changes on Earth over the past 2 centuries, many of them as a result of increases in human population. Global climate change causes and consequences will also be looked at. You should know the differences between global change, global climate change, global warming. This figure depicts factors affecting change in warming. Global climate change refers to those factors that affect average weather in an area. Global warming refers to changes in temperature over an area. Global change is all about additional factors that may be chemical, biological, and physical. Remember that global climate change can be natural and anthropogenic. Natural causes in climate change include, for example, El Niño. Anthropogenic changes include fossil fuel combustion. Anthropogenic causes include fossil fuel combustion and deforestation. This chapter and this presentation focuses on global climate change. This figure depicts some of the physical and biogeochemical systems that regulate temperature at the surface of Earth. It is critical we understand how exactly the planet is warmed by the sun, and how sources of radiation are converted into other sources of radiation, and how the greenhouse effect contributes to the warming of Earth. Can you describe the steps or processes involved in the warming of the planet using this figure of the greenhouse effect? Pause, think, write it down, and then press play again to check your answers. The greenhouse effect is when the high-energy radiation from the sun strikes the atmosphere. About 1/3 is reflected from the atmosphere, clouds, and to the surface of the planet. Much of the high-energy ultraviolet radiation is absorbed by the ozone layer, thank goodness, where it's converted to low-energy infrared radiation. The remaining ultraviolet radiation and visible light strike the land and water of Earth, where they are also converted into low-energy infrared radiation. The infrared radiation radiates back toward the atmosphere, where it is absorbed by greenhouse gases that radiate much of it back toward the surface of the Earth. Collectively, these processes cause warming on the planet. In the Sun-Earth heating system, the net flux of energy is 0. The inputs of energy to Earth equal the outputs from Earth. Over the long term, thousands to millions of years, the system has been in a very steady state. However, this chapter focuses over the years or decades, inputs can be slightly higher or lower than the outputs. Examples include changes in incoming solar radiation, increases in atmospheric gases that absorb infrared radiation. So these are your major greenhouse gases, the major ones. You must know these, you must know these, you must know these. Certain gases in the atmosphere can absorb infraradiation emitted by the surface of the planet and radiate much of it back toward the surface. Greenhouse gases are those that absorb infrared radiation. The 2 most common are nitrogen and oxygen. These are not greenhouse gases. They're the 2 most common gases. They comprise 99% of the atmosphere. They do not absorb like greenhouse gases, and do not contribute to the warming of the Earth. But water vapor is a greenhouse gas, and it absorbs more infrared radiation from Earth than any other compound in the atmosphere. As you can see from this chart, though, water vapor does not persist as long as other greenhouse gases. Notice CO2, methane, which is CH4, nitrous oxide, and ozone, O3, persist much longer. And CFCs do not exist naturally and occur in the atmosphere exclusively due to synthesis by humans. And oh, by the way, some people think ozone is only a bad greenhouse gas. Ozone is indeed very harmful to plant and human respiratory systems. It is also an air pollutant in the lower troposphere, the layer which we live in and the planes fly in. It acts as a greenhouse gas in the troposphere, but it's a good guy in the stratosphere, which is the next layer up. There, it's beneficial because it filters out harmful UV radiation. The greenhouse effect is regularly known as a bad guy, but naturally, it's not. The anthropogenic enhancements to the concentration of greenhouse gases may cause the planet to warm even more. We are the bad guy. So think about, what would the average temperature of Earth be without the greenhouse effect? It would be really, really cold. We need the greenhouse effect so that we don't go into sub-zero temperatures every single night. This figure started out as a series of photographs taken from satellites. The red line, labeled as the Arctic sea ice boundary, is a tracing of a satellite image taken in 1979. The white inside the boundary is what was taken in 2010. More than 20% of the polar ice cap has melted away. Looking at this chart again, you can see the warming potential of certain gases. Using scientific experiments and modeling, scientists have determined the potential of a molecule for each gas to contribute to more warming of the planet. Methane, for example, has a warming potential 25 times higher than CO2, which gas is in this chart, which gas is the greatest contributor to the greenhouse effect. Because of its concentration being so much higher than any other gas, CO2, as a result, policymakers focus their efforts on reducing CO2 more than any of the other gases. Look how high that is. And by the way, this book was printed in 2012, and we are officially over 400 parts per million of CO2 in our atmosphere, so we're steadily climbing. Notice in 2009 how the U.S. distribution of greenhouse gas emissions looks. Don't think you are not counted in agriculture. Do you grow, harvest, and raise your own food sources? Transportation, do you own a car? And then look at what you contribute just inside your own home. Do you use hairspray and cleaning products? Lawn mowers? Leaf blowers? Do you have chemically treated furniture and carpeting? Well, then you're emitting greenhouse gases. Sources of greenhouse gases are natural and anthropogenic. We're going to focus on natural sources for a moment. They include volcanic eruptions. Now, a lot of people, if I ask you the question, what does a volcanic eruption emit as a greenhouse gas, you immediately go to what you remember in air pollution, and you answer sulfur dioxide. No. Volcanoes emit the greenhouse gas CO2. That is the one they emit to the atmosphere. That's a greenhouse gas. They also add ash, which reflects incoming solar radiation back into space. It just kind of blocks it, and it cools the Earth. One eruption's ash can cool the planet by 1 degree for a few years. Then the particles settle out. Ash is not a greenhouse gas, however. Remember, it wasn't on the list. CO2 is. Sulfur is also emitted, which is not a greenhouse gas. CO2 is. All right, this slide's about methane, or CH4. So starting with this picture to the left, look at the termite mound. How do we get methane from termites? The bacteria that live in the anaerobic gut of termites produce methane as a byproduct of the digestive activities. Because of their population size of more than 1 million per colony, they produce very large amounts of methane. A methane gas bubble in a wetland is to the right. This occurs due to anaerobic activity. Wetlands are the largest natural sources of methane, where plants and animals decompose, and oxygen is in low supply. Low oxygen or no oxygen means anaerobic, and we're going to get the methane from that. Now look at the chart to the bottom. Notice the natural occurrences of methane and the anthropogenic occurrences of methane. You already should know all about landfills, and you should know a lot about what fits in these categories. Landfills contribute methane when there's not enough oxygen available to produce CO2. Rice paddies act like wetlands. Rice is grown in a way where the rice is flooded, so plants decompose without oxygen, releasing methane. Nitrous oxide that's N2O, is a natural component of the nitrogen cycle produced during nitrification. It is the laughing gas that dentists use. Denitrification occurs in low oxygen environments of wet soils, like permafrost that's melting, and at the bottoms of wetlands, lakes, and oceans. When this gas forms, it enters the atmosphere as, from the list, a powerful greenhouse gas. Water vapor is the most abundant greenhouse gas in the atmosphere and the greatest natural contributor to global warming. We can't really work with water vapor like we can with CO2. We can't control it as much and as easily. Know your hydrologic cycle. The examples of climate feedback are important to understand. These are definitely things you would be asked on a test, not like what is the next step in the water cycle or hydrologic cycle. They might ask you about where we are impacting the feedback system. Feedback loops are processes that increase, remember this, positive is always increase or decrease change to a system. In environmental science, when we look at feedback loops, we're looking at the positive, and positive is not good. A feedback loop occurs when an output of matter, energy, or information is fed back into the system as an input and leads to changes in that system. A positive feedback loop causes a system to change further in the same direction. An alarming positive feedback loop is the melting of polar ice, which has occurred as the temperature of the atmosphere has risen during the past few decades. As that ice melts, there is less of it to reflect sunlight and more water that is exposed to sunlight. Notice more and more. Because water is darker than ice, it absorbs more solar energy, making the polar ice warmer and causing the ice to melt faster. Notice these are all increases, thus exposing more water. The melting of polar ice is therefore accelerating, causing a number of serious problems. This example of an accelerating positive feedback loop can reach a breaking point that can destroy the system or change its behavior irreversibly. Here's another example of anthropogenic sources of greenhouse gases. Human activities are major contributors of GHGs, including CO2, methane, nitrous oxide, and others. I just named some. So what are the activities causing this contribution of GHGs? Well, these are it. Now, can you guess which anthropogenic activity shown produces which greenhouse gases? Pause for a minute. Guess which greenhouse gas belongs with which. Examine the charts here showing anthropogenic sources of greenhouse gases in the U.S. The first chart shows the largest contribution of methane in the atmosphere. Do you remember what livestock digestion has to do with putting methane into the atmosphere? Hopefully you guessed there's something to do with the gut bacteria. So the gut bacteria that help many livestock species digest that plant material that they eat in the cellulose, gut bacteria live in a low oxygen environment. And digestion in this environment produces, because low oxygen anaerobic, produces methane as a byproduct. And if the manure or poop from livestock is exposed to high oxygen conditions, it will decompose to CO2. In low oxygen conditions, the manure will decompose to methane. Rice fields that are over-irrigated or deliberately flooded for cultivating crops create low oxygen environments similar to wetlands and therefore produce methane and nitrous oxide. N2O. I had that wrong in that slide. I knew it. Now, glance at the top 3 sources for each GHG in the U.S. Look away. What's the top contributor to CO2 in the U.S.? Now look. Check your answers. The combustion of fossil fuels. We're putting CO2 back into the air at a much faster rate than producers take CO2 out of the air. Now look away. What are the top 3 sources of nitrous oxide? Now look. The top is agricultural soils. What does that mean? What would soils and agriculture have that contributes to greenhouse gases? We add fertilizers, manure, and nitrogen-fixing plants, such as alfalfa, which converts nitrogen to nitrous oxide. This is the process of denitrification. Remember your cycles. All right, I'm going to ask you another one. Get ready. Glance at everything. Now look away. What are the top 3 contributors of methane, which is CH4? All right, now look. Livestock digestion, landfills that are not aerated to assist with decomposition, and the production of other fossil fuels such as natural gas and petroleum. Make sure you know this chart, study it well. Know what belongs and what doesn't belong to each one of those. Now we know something about greenhouse gases and their role in global warming. We still need to explore the evidence that an increased concentration of greenhouse gases is causing Earth to become warmer. So we know it's getting warmer. but we need to have the evidence that it's because of us. We need to determine if human activities are causing this trend. One way to make this assessment is to determine gas concentrations and temperatures from the past and compare them to today. We can also use this information to make models and predict future climate change. Global climate change has been very controversial, so let's explore why, starting with charts. We now understand that CO2 is an important greenhouse gas that can contribute to global warming, but we didn't always realize this. Scientists believed not too long ago that excess CO2 would be absorbed by the oceans and vegetation. Also, since CO2 concentrations are so low compared to oxygen and nitrogen, technology made it really hard for us to measure accurately. New scientific methods imagined by this guy Charles Keeling showed us that CO2 levels varied seasonally. That's a little purple line going up and down, and that the concentration of CO2 increased from year to year, which is the blue line. He studied this in Hawaii. That's where he collected all the atmospheric data, and the results are in this chart. The blue line is basically the average over the year. The peaks and valleys of the purple monthly averages show the seasonal differences. There's an increase over time caused by human combustion of fossil fuels combined with the net destruction of vegetation. Think deforestation. What do you think causes the seasonal variations? The purple going up and down, up and down. All right, well, here it is. Spring plants and trees increase their absorption rates of CO2, think photosynthesis, to carry out the process of photosynthesis. Think about the winter when we don't have as much photosynthesis occurring, and we have more fossil fuels used for heat, contributing to more CO2 in the air. Producers take up some of this CO2 in the atmosphere. In the fall, leaves drop, crops are harvested, and production declines, thereby not taking as much CO2 out of the atmosphere. Other things to consider with this chart that would come up on the AP test. You might be asked to calculate the percent change between like 1980 and 2010. Do you remember how to calculate this? Between 1980 and 2010. You have to make sure you do. So here's how you calculate percent change. Remember, you take the difference between the two, and then you divide by that original piece of data. So practice it a few times. What do you think the percent change was between 1980 and 2010? Go ahead and pause. Okay, so you should have, from 1980 to 2010, determined there was a 55 part per million difference. Then 55 divided by 335, which was your original, gives you about a 14% change. All right, this is an opportunity to estimate how much CO2 concentrations will increase by the end of the century. I want you to pause after I say a little more, pause this presentation, and work out problems 1 and 2. Do this by reading the box, setting up the work already done for you, then finishing the work. Make sure you show your units and numbers neatly and correctly. Press pause. Okay, here are the answers for the problems that were just shown. I hope you practiced. Check your work here. Press pause to check it more carefully. We've been learning that per capita consumption of fossil fuel and materials is greatest in developed countries like us. Unfortunately, developing countries are surpassing us in production of CO2. Look for China and India. How much of the world population do they contain? Well, they contain 1/3 of our population. That's huge. As you can see, China is also the world's leading emitter of CO2. They emit more than 6,500 million metric tons of CO2, representing 21% of all global emissions. The U.S. emits 19% of all global CO2 emissions, but we only contain 5% of the world's people. But if you look at China in per capita, we see that a very different picture of which countries produce the most CO2 really is. Because the populations of China and India are so large, on a per capita basis, they rank as the 16th and 20 leading emitters. It's all about perspective. All right, you should know how to read this chart, and you should know how to tell the trends that are happening. Global temperatures since 1880 are what we're looking at here. We see here that global temperatures have increased 1.4 degrees from 1880 to 2009. And 9 of the 10 warmest years were most recently, making the last decade the warmest on record. Oy. Notice the blue line. The average temperatures for each year for the past 5 years shows definitely a much clearer pattern. All right, what does this map show us? What trends do you see? What anomalies do you see? Anomalies are just things that don't fit the patterns. Can you explain them? You should pause and you should think about this and list them. And then I'll replay. All right, so what you should have determined is some regions, including parts of Antarctica, have experienced temperatures that are cooler than experienced in earlier years. Some areas of the oceans have experienced no change in temperatures. Some, such as those in extreme northern latitudes, have increased from 2 to 7 degrees Fahrenheit. All right, this map and many others like it clearly demonstrate that the globe has been slowly warming during the past 120 years. However, it's possible that these changes are natural phenomena. We must dive into longer records, look back even further in time if we really want to know if this is typical or if it's human caused. This is not enough evidence to debate over the controversy if humans are the cause of unwanted climate change. So here's how we gather our evidence that we are the culprits. We start with ice cores. These are pretty cool. Ice cores can be extracted from very cold regions. They trap air bubbles of ancient air that can provide indirect estimates of greenhouse gas concentrations and global temperatures. Keep in mind that these ice cores are in places where the ice snow just falls, packs into ice as more layers compress, and it never melts. Scientists drill really deep. They have cores up to 500,000 years old. All right, here's an ice core up close. They melt a little piece of ice from a particular time period, and they capture the gases that escape as it melts. They then quantify the atmospheric composition in parts per million. That's pretty cool stuff. Oh, and they know how old a portion is based on the radioactive decay of other particulate matter. So here's that dirty little greenhouse gas CO2 data from the ice core. Examine the concentration in 2010. So it's 390 parts per million. Well, actually, now we're over, because we're 2015, we're over 400. And compared to years before present, remember this data was found in ice cores, the trapped bubbles. Remember that. Let's practice some quantitative skills. Use the graph to determine the net change in atmospheric CO2 concentrations between 100,000 years ago and present day levels. Pause and calculate. We're looking for the net change. All right, so your answer should have been 160 parts per million. We calculate for net change by subtracting 230 from 390, which was around 160 parts per million. Increase in CO2 concentration over the past 100,000 years. Come up with another question and answer that could show up on the AP exam based on this chart. You definitely should have asked about a percent change from one point to another point. That's likely to come up. All right, so we're still looking at ice core data here. And scientists have demonstrated that atmospheric greenhouse concentrations have increased dramatically during the past 200 years. So now we're just looking at the past 200, basically since the human industrial revolution. We're looking at the zoomed in data from the last slide. Notice how much nitrous oxides, CO2 and CH4, are in the atmosphere. And notice how much it has changed since the Industrial Revolution. We know it's us from all the other chapters of evidence about energy production, agriculture, deforestation, and air pollution. We know it's us that's causing this. All right, I'm not going to go over all the answers because this will take forever, but you can very easily just think about your notes and the things we've done and answer the questions. If you have any questions about the difference between these, you can see me. You should know this. Remember these, always and forever and forever. All right, now right here, we're looking at ancient shells of foraminifera because this is another piece of evidence that we use to show that the oceans have been warming over time. So we know what the different foraminifera are today, and we know how sensitive they are to changing temperatures in the ocean. So some will only live in certain temperature ranges, and if it gets any cooler or any warmer, they can't exist in that temperature range. So what we do is we dig up fossils from ancient sea or ocean beds, and we look for foraminifera. Remember that the layers on the bottom are older than the layers above it. So we take the foraminifera from this time period and that were trapped in this time period, and we look at foraminifera that are like them from today, and we determine, oh, okay, we know that the ones that are today that are just like these organisms can only live in this temperature range. So the temperature of the ocean had to be within this range during this time period. And then we do the same thing for other time periods. And that's been our indirect evidence from a paleoclimatologist's point of view of what the temperature of the ocean was in the past before, or since humans have been here and before humans have been here. That's a pretty cool job, right? So remember, this is all using relative dating techniques. oldest rock and organisms here are the oldest. All right, if you have the time, check out these links, Bozeman Science Greenhouse Effect, and also go to the PHET Colorado simulation on greenhouse gases, and you'll be able to see the little molecules of the greenhouse gases and what they do when the solar radiation or photons affect them. Now, here's another graph, another one that we use to help support that humans are definitely not the only things that have caused climate change. We have gone through changes all through the past. So we're going to follow the CO2. CO2 is going to be your purple line, and temperature is your blue line. So we've used ice cores. Ice cores, remember, the ice doesn't melt, but it traps the atmosphere in with it. We've measured ice core data, and we've looked at just CO2, and we've looked at just temperature. We don't find temperature in there. We find evidence of things that can tell us what the temperature was. So ice cores have measured factors of climate, temperature. We've looked at CO2. Look at the close correspondence between historic temperatures and CO2 concentrations. And remember, this has happened before humans were here, so these are indirect evidence. The graph does not tell us the nature of this relationship, like which factor caused which change. Is there another factor at work? It doesn't tell us that. They believe the relationship between fluctuating levels of CO2 and temperature is very complex, and that both factors play a role with each other. As we already know, the increase of CO2 in the atmosphere causes a greater capacity for warming through the greenhouse effect. We know that. What ultimately matters is the next movement of CO2 between the atmosphere and the oceans, and how these different feedback loops work together to affect global temperatures. This shows that average past temperatures remained cooler than the average during the 20th century. It's interesting that the change in temperature during the past century has increased rapidly, and the average temperatures that we are experiencing today are higher than those experienced in the past 2,000 years. One explanation for warming temperatures during the past century is an increase in solar radiation. Another possibility is that warming is caused by increased CO2 in addition to warming caused by natural fluctuations in solar radiation. But the IPCC has concluded that if increased solar radiation were the culprit, we would see more warming in the lower latitudes than in the polar regions. So, can't be just that. All right, this shows the predicted increase in global temperatures by 2100. The predictions depend on whether we expect low, moderate, or high increases in how much CO2 the world emits during the current century. This is a climate model, and it helps us predict future climate conditions. This is not totally accurate, but they practice using the logarithms and other statistics on past data we can already confirm, to support the model. The more models that agree and predict similar changes, the more confidence we have in the predictions. And there's a lot of models that are confident in those predictions. We have looked at these before. These are feedback loops. Feedback can increase or decrease the impact of climate change. Positive feedback loops amplify change. Because of this, positive feedback often leads to an unstable situation in which small fluctuations in inputs lead to large observed effects. Positive is not good in environmental science. Global soils, for example, contain more than twice as much carbon as the amount currently in the atmosphere. As shown, higher temperatures are expected to increase the biological activity of decomposers in these soils. This decomposition leads to the release of additional CO2 from the soil to the atmosphere. With more CO2 in the atmosphere, the temperature change will be amplified even more. Oh my gosh, more and more and more and more. More troubling is the expected tundra biome, which contains permafrost. As CO2 increases, Arctic regions warm, frozen tundra begins to thaw. The tundra develops areas of standing water with little oxygen available under the water as the organic layers begin to decompose. Anaerobic decomposition occurs. This decomposition produces methane. Methane is a stronger GHG than CO2. This should lead to more warming. Positive, amplifying the changes. Plants respond to atmospheric carbon because CO2 is required for photosynthesis. An increase in CO2 can stimulate plant growth. More plants will cause more CO2 to be removed from the atmosphere. And this negative feedback causes carbon dioxide and temperature increases to be smaller than they otherwise would have been. This is why only half of the CO2 emitted into the atmosphere by human activities has remained in the atmosphere. So thank God for some negative feedback loops. We're almost done. Global warming has serious consequences for the environment and organisms. Can you list all the consequences? Think. Brainstorm for a minute. Consequences to the environment of global warming. All right. Did you write some down? If you didn't, pause. So here we go. Melting of polar ice caps, glaciers, melting of permafrost, rising sea levels, increased frequency of heat waves, reduced cold spells, altered precipitation patterns, and storm intensity, and shifting ocean currents. These are all consequences that are very serious of global warming. This image shows the melting of polar ice caps. The first image was taken in 1980. The last image was in 2010. The area of ice lost is almost 3 million square kilometers. That's awful for polar bears and Arctic foxes, isn't it? This only includes area. Of course, if the sea ice opens ocean areas, we could have more shipping routes, though, more direct ones. We could also access more fossil fuels. So is this good or is this bad? Here is Glacier National Park in northwest Montana. Had 150 glaciers in 1850, and now there's only 25, and they're expected to completely disappear by 2030. So if you want to see some glaciers at Glacier National Park, you better go soon. Melting of permafrost causes lakes to become smaller as the lake water drains deeper down into the ground. Human-built structures that are anchored into permafrost can have problems, including houses and pipelines. Ground can subside and slide away. Melting of permafrost will also cause decomposition of massive amounts of organic matter in wet soil under low oxygen conditions, releasing lots of methane. So creating positive feedback loops in which the warming of the earth melts the permafrost more. The pics here, these pictures, show problems with melting of permafrost in a parking lot and a forest. Remember, permafrost is in the tundra biome. Permafrost is one of the characteristics that classify biome as tundra. All right, we're looking at an island here. We'll get back to that in another slide. But look at the chart. Sea level has risen how many millimeters and inches since 1870? This is a typical question on the AP exam. So pause and try and answer. How many millimeters and inches since 1980 has sea level risen? So did you say 220? Well, you're right if that's millimeters, but make sure you convert your millimeters to inches. With about 25 millimeters in an inch, that makes it 9 inches. Sea level has risen 9 whopping inches since 1870. That's huge. Scientists predict a rise in another 23 inches by the end of the 21st century. This will do the following. It will endanger coastal cities and low-lying islands, such as this one, causing more flooding and more saltwater intrusion into aquifers, and cause an increase in soil erosion. So how can we mitigate this? Well, we can build up our shorelines with dikes, levees, and dune restoration. All right, we're going to do another, you're going to read this, you're going to practice your quantitative skills for this problem, and you should be able to complete it in about 4 minutes. Pause the video and make sure you show your work and label everything, then check. All right, grade your work. If you're not able to read it and correct it in 1 minute, it's too sloppy and should be given a 0. This is the island of Maldives, which was just shown on the previous slide, in the Indian Ocean. This island will be underwater if our trend continues by the end of the century. It will be underwater if the sea level continues to rise as predicted. All right, other things because of global warming. We're going to get heat waves. Well, we know we are. They'll become more common with increased global warming. This requires an increase in energy for cooling. This will cause health risks to the elderly and or the poor. Heat waves also cause drought and heat damage to crops and demanding more irrigation, raising the cost of food. Cold spells are going to be less common with global warming. This would have 2 major positive effects, actually, for humans. So cold spells will be less common. We'll have fewer deaths due to freezing temperatures, and will decrease the risk of crop damage from freezing of the crops. Could make new areas available for agriculture, although many pests are limited by cold temperatures and will spread as a result. We will probably wipe out other organisms, such as the hemlock trees and these woolly invasive insects from Asia, which won't be able to tolerate the change in temperature. Ha. All right, warmer temperatures equal increased evaporation equals more precipitation equals higher crop yields, which could equal more aquifer recharge, but some places will experience more drought due to shifting weather patterns. Storm intensity can increase, especially in the Atlantic hurricanes, because of the recipe for a hurricane. Hurricanes require warmer ocean water and warmer temperatures, and the Atlantic Ocean is warming. Hurricanes are likely to go further north, just like Hurricane Sandy. All right, global ocean currents may shift also. They affect climate. They could become less salty due to melting ice. Thermohaline circulation, which is shown here, could stop. This would cease giant ocean circulation of cooler waters toward the equator and warmer waters to the higher latitudes. Europe could actually get a lot colder as a result of this because of the change in thermohaline circulation. Living organisms, such as this pied flycatcher from the Netherlands, adapt behaviorally to seasonal changes, which could greatly impact the survival of their offspring and the food they eat, like caterpillars. Animal and plant disbursement, flowering, and habitat requirements can be altered to a point that these guys can't survive. So the IPCC determined that plant growing seasons have lengthened. Plants flower earlier, birds arrive at their breeding grounds earlier, and insects emerge earlier. Ranges occupied by different species have shifted toward both poles. The migration of species is not a problem as the climate is warming slow enough for them to adapt. But humans are causing a problem with this migration because of all the defragmentation. We are not helping with the movement and migration of species. Corals are organisms also particularly sensitive to global warming because their range of temperature tolerance is very small. Coral bleaching, which occurs when stressed corals eject algae, providing their energy, and they turn white, is occurring worldwide. The causes appear to be a combination of warming oceans, pollution, and sedimentation. Sometimes bleaching is temporary. This is an example of coral bleaching. Many times it's too long and they die. This montage of pictures shows what coral life should look like and the sad pictures of bleached coral. This is coral bleaching here. You know that most coral are animals, right? They filter and feed phytoplankton. Humans have been greatly impacted already by our own demise. We've had to relocate from vulnerable areas. Tourism at ski resorts has declined due to lack of snowy mountains. Diseases are spreading more, especially those transmitted by tropical insects and other temperature-related disease vectors. Bacteria and fungal illnesses are spreading more easily. So the IPCC has assessed and determined these are the top 7 changes that humans have caused and the trends that will occur as a result of global warming, human-caused global warming. Now study and know the IPCC top 7. And make sure you understand the trends and the likelihood of the trends. So then there's the Kyoto Protocol that we've talked about before, and that addresses climate change at the international level. It's an agreement by nations of the world to cut down on global emissions of greenhouse gases. The United States is actually not in full agreement due to other political pressures and economics. The Senate voted unanimously that the U.S. should not sign any international agreement that lacked restrictions on developing countries like China or that would harm the U.S. economy. Clinton signed it without Senate approval or ratification, so our signature is not legally binding. The U.S. have agreed to different levels of emissions restrictions anyway, including a 7% reduction. The other mission of the protocol, the Kyoto Protocol, in addition to reducing emissions, is to take measures to remove the gases from the atmosphere. For example, one of the measures we could take to remove what we've already put in there is switching from coal and oil to natural gas, solar energy, wind-powered energy, nuclear energy. The second option includes this thing called carbon sequestration. So see this image now. This is where we're showing carbon sequestration. It's an approach that involves taking CO2 out of the atmosphere. Methods might include storing carbon in soil or compressing the CO2 and pumping it into abandoned oil wells or deep oceans. It doesn't matter so much about the Kyoto Protocol and that we're not officially on paper signed and agreed to everything. We're still trying to practice many of the parts of it. Many states are taking steps to limit greenhouse gas emissions in several ways. California has actually been the most proactive, and other states are following suit. So go USA. All right, so this was, if you did not accelerate the speed of the video, this was all of Chapter 19, Global Change, in less than 40 minutes. Make sure you repeat, play it in your sleep, do whatever it takes to really understand everything and the factors about climate change versus global change. This is Ms. Gabriel signing out.